Hello everyone and welcome back to our series on urban energy modeling with Dragonfly. And in this video, after many of you asked for it, we're going to cover the workflows for running your Dragonfly, urban scale Dragonfly models through an engine called the Urban Weather Generator, which will allow us to account for the effect of urban heat island. Now, for those of you unfamiliar with urban heat island, it's the condition where the urban area is a few degrees warmer usually than the surrounding rural area. And it occurs most intensely typically at nighttime, usually after sunset. And the urban weather generator is an engine that was built to morph EPW weather files, so weather files typically coming from an airport or a rural area, and take a set of properties for a given urban area and morph that EPW file to account for the effects of urban heat island, the urban heat island effect. So in this video, we're going to actually use a Dragonfly model in order to morph an airport EPW and understand the impact of urban heat island. These EPWs that you morph can be used for a wide variety of purposes. They can be plugged into energy simulations if you want to account for energy use under the effects of urban heat island. They can use for comfort studies and many other capabilities. But in this video, we're just going to try and morph the EPW and visualize it in the scene. So first things first, we're working with this from building solid sample file. The way that you can get this file is there's a link in the description, but you can also just go to our Ladybug Tools samples repository, go into the samples folder under Dragonfly, and in the Rhino subfolder you'll find this from building solids.3dm file. So this is what we're working from here. And I'm doing that because this is a relatively high density neighborhood, and those of you who are familiar with urban heat island probably know it's much more intense in urban areas that are higher density, so we should hopefully be able to see some effects here. So I'm going to go ahead and open up Grasshopper so we can start to assemble a kind of minimal Dragonfly model that we can use for our urban heat island simulation workflows. So let's see. First things first, with a blank Grasshopper file here, I'm going to use our from building solid workflow in order to convert these solid geometries in the scene into Dragonfly buildings, which I can then merge into a model. And we covered this extensively in earlier videos in the series, so I'm going to go pretty quickly through it. But essentially, I'm just going to take select our objects for our office buildings. I'm going to bring them into Grasshopper using a native Grasshopper geometry parameter. With everything selected in the Rhino scene, I'm going to right click and say set multiple geometries to bring them into Grasshopper here. I might as well internalize them, and I'm going to turn the preview off so we don't see too many of them. And I'm going to connect that to my building geometry here. For our floor-to-floor height, I'm just going to do something simple. Maybe all the stories will be at 4 meters tall. That seems good enough, right? So that'll divvy up the building all the way 4 meters to the very tallest height of the building. And I guess our program for these blue buildings, I'll set this to office, to a large office building. So I'm just grab our building programs, drop down list from Honeybee Energy and connect. Yeah, it's already large office. I could have selected these other ones, but I'm just going to plug that in for our program. Okay. Oh, and probably one other thing, I should do diligence and just set a construction set that's cognizant of the climate. So I'll just grab my HB construction set by climate, plug in. I mean, I guess in this case, maybe I know this model that we worked with previously is in Boston, but if we really want to understand the impact of urban heat island effect, I think it's going to be much more impactful to look at a climate like Phoenix, Arizona, or a desert climate like that. So I'm going to actually select a hot climate zone here, which I know this is climate zone 2 is the one that Phoenix, Arizona is in. So, all right. So I'm actually just going to copy this into a panel because that's really all that I need in this case. I just need the text and I can plug that in for a construction set. And lastly, we need just a Boolean toggle, set that to true and connect it to this component. And we will have our Dragonfly buildings ready to go. Okay. So, all right, again, this is all review. We covered this in an earlier video in our From Building Solids workflow video. So I'm not going to beat around the bush too much with this. I'm just going to bring in the other geometries I have here. I'm going to bring in our these residential buildings as from solids as under the mid-rise apartment program. And I'm also going to bring these solids. I know we kind of modeled these as context shade previously, but I'm going to bring them in as just maybe like they're just parking garages, so maybe I'll just use a very simple warehouse or something typology, because I still want to account for them as building geometry within my urban heat island simulation. So all right, so I'm going to fast forward to the next part so that you guys don't get bogged down by the repetitive nature of this. But essentially, I'm just going to be importing the buildings using the same methodology that we did here. Okay, see you in a minute. Okay, so we now have our Dragonfly buildings all set up, right? They're being derived from our building solids. We have our commercial buildings or our large office buildings. We have our residential buildings, which are just being modeled as mid-rise apartment, and then we have these kind of structures that are not really very energy intensive that I'm just modeling with a warehouse here. And you can see I'm being much less careful in the way that I set up my model here than I was when I created an energy model. And that's because when you model the urban heat island effect like the way that we're doing here, honestly, I mean, as long as you're getting the building loads approximately correctly, you're gonna get pretty much the same results. The critical things that really impact urban heat island are the geometry, but essentially the density of the site has a huge impact on that. Things like the traffic and the amount of kind of what we call anthropogenic heat, the heat generated from cars, can have a very big impact on urban heat island effect. And of course, things like vegetation, reflectivity, the type of pavement, those all have a really big impact on the urban heat island. So that's why I'm being much more loose with the way that I'm assigning programs and everything to these buildings because most importantly, I just want to get the geometry correct. So all right, so now that I have these buildings, I'm going to join them together into a Dragonfly model. Although I just realized that I forgot to do one thing, is that probably what can have a relatively significant effect is the glazing ratio. So I'm going to add some window parameters just to these buildings. They're going to be very, very simple. I mean, I'm just going to do something like 60% glazing for these office buildings, and I'll assign those with the um, whatchamacallit, the DF apply facade parameters. And actually, I just realized, here we go. Let me help everybody out here so that they can see a little bit better which components I'm actually using here. So, all right, so I just pulled up my little app that allows you to see the names of these components. So I'm using DF apply facade parameters and DF window by ratio. So this way I can assign window geometries to my buildings. So I'll just copy paste this very quickly, so we can assign a window ratio of maybe we'll say like 2.25 for our residential buildings because they don't need nearly as large windows as you'd find in an office. And then, I mean, this could really be anything. Our warehouse geometry here, maybe I'll just set it to zero point 0.4. It's really more like an open air structure, but I think this is good enough. All right, so we've got glazing ratios assigned to our buildings. I'm going to bring all these buildings now together into a Dragonfly model. All right, I'm just going to connect up the edited buildings that we're getting out of these facade parameters, connect those up to the buildings of the Dragonfly model. Okay, all right. And now we're accounting at least for all the buildings in the scene here, right? And so the way that we're actually going to run the urban weather generators with a component under the alternative weather section here, I realize we haven't touched this section up until this point, but most of the components you're going to see under this section 4 here are meant to help you run your Dragonfly models through the urban weather generator. At least half of them, I'd say, are for that purpose. And importantly, this DF run urban weather generator, this is what we're actually going to use in order to morph an EPW file for the UWG here for urban heat island effect. And you can see I can just go ahead and straight up take my model and plug this into here. Every Dragonfly model that you create is suitable for export to the UWG. There are a few parameters, however, that I'd recommend tweaking before you go and simulate. I listed them a bit earlier in the video, right? That the density of the site is very important. So it's actually fairly important to specify what the kind of ground terrain surface is for your urban area, because otherwise, I mean, Dragonfly will try and auto-generate that surface, but if you can specify it yourself, you'll get a much better reading of what the density is of your urban district. So I'm going to specify that terrain right now by taking a component here called, here we go, df assign model UWG properties. So what this allows us to do is that we can actually take our Dragonfly model and we can assign a terrain object to it, right? So that we can actually get a better estimate of density. And actually, if you see what this input is meant to accept, it's the output of another component called the df terrain component. If I drag and drop this Dragonfly terrain component on my canvas, we can actually use it to specify not just the geometry of that terrain, but also things like the albedo of the concrete and or asphalt that may be on the ground of this urban area, among a bunch of other things. Now, I think I'm going to leave all these as defaults, but I do want to specify a terrain geometry here. So I'm going to double-click the canvas and type, bring up a native Grasshopper geometry parameter. And with this terrain surface selected, it's just one surface you can see here. I'm going to right-click on the this geometry parameter and say, we can just say set one geometry, that's fine. And that'll bring that into Grasshopper here. Might as well internalize it and turn the preview off. You know, not required, but that at least keeps my Rhino scene a little cleaner and this Grasshopper definition independent of the Rhino document. So, all right, so I can connect up my terrain geometry here. I can connect up then this terrain geometry to here. And we should actually see, I think the report of this component, yeah, it's actually giving me some fairly useful information. Right, so we can see it's telling me the average height of the buildings in this urban district is 33 meters. The footprint density, right, that's the density value that I said can have a big impact on urban heat island effect. So that's almost about half of the surface, the terrain surface is covered by building footprints. And then we have a facade to site ratio, which is basically, yeah, how much facade area is there along these buildings here. And you'll notice one other thing, actually, it's probably important for us to change is this tree cover and the grass cover. And the way that we can do that, you can actually specify numbers for tree cover and grass cover on this model UWG properties. So if all you want to test out is like, what if we cover, 50% of the ground surface with tree cover, you can plug in a value here and actually just immediately test the impact of that on urban heat island effect. There's another way that you can actually specify vegetation cover, though, and that is through actual context geometry. So you see we have all of these actual terrain, well, all these shade surfaces for trees. What I can do within the UWG workflows here is that I can bring in these tree geometries with a native Grasshopper geometry parameter. I'm just going to select all the trees that I have here. These select objects, right-click on the layer, say select objects, and I'm going to bring them into Grasshopper here. Setting multiple geometries, same workflow I used everywhere else. And might as well internalize and turn the preview off. Okay, but with these actual geometries, with all these 178 tree geometries, I can turn these into Dragonfly context shade, right? By just passing them through this component here. And there is a property that we didn't really cover in our earlier videos that is useful specifically for this purpose of trying to account for vegetation cover. And this is that you can say, set the property of whether this geometry is meant to represent vegetation. So if I take a Boolean toggle and I set this to true for this UWG is veg, and then when I connect up this context to my Dragonfly model, so I can account for it in my, as part of the simulation, right? What we'll actually see now is, yeah, so the tree cover has changed from being 0 to about 10% or 0.1. And that's all because I specified this UWG is veg property on the context shade here. So you have two options for the way that you want to model vegetation. You can either specify tree cover and grass cover here, or you can actually take the geometry. And you'll notice if I set this to false, right, the tree cover is going to go back to 0. It's going to assume that this is not vegetation. But setting it to true, right, you can actually, extract that tree cover from the geometry there. Okay. I think we got something good enough here, right? We've got a model. Maybe one other thing I will say, you heard me say in the beginning that the traffic can be very important for urban heat island modeling. And so you can tweak that by using this DF traffic parameters component. This allows you to set the watts per area of street, that basically the density of energy consumption with traffic. And maybe if I want to see something big here, I can set this to a number like 25 watts per square meter. I mean, that's probably a pretty high density. You can see we have some other estimates for typical commercial areas or residential areas. And you'll see you can also tweak the schedules of these of this traffic. But let me just say, I'm going to say this is a pretty busy district, we'll assume. There are 25 watts of traffic per every square meter. All right, now we've got our model. Basically, it's the same. This is a Dragonfly model, just like the things that we used for energy simulation. But I've now tweaked a lot of the urban weather generator properties such that it's a bit more meaningful for this urban heat island simulation that I have here. So, all right, I'm going to go ahead and connect this Dragonfly model up to our DF run urban weather generator. And you'll see if we look at this, there are two other required inputs. We need to get an EPW weather file. And the easy way that I'll do that is just by going to our EPW map interface, which you can see, well, it should be the top Google result most of the time. And I'm going to take the weather file for Phoenix, Phenix. Oops, don't know how to spell Phoenix. Well, you know what? All right, I'm just going to take a shortcut. Yeah, here we go. Phoenix. All right. Learn to spell, Chris. All right, so let me grab a weather file from Phoenix here. Let's see, we'll just maybe take the one from the Department of Energy, Sky Harbor. This seems good enough. And I'm going to drag and, once I've copied the URL of the Phoenix weather file to my clipboard, I'm going to bring up a panel by double-clicking, typing double quotes, and then pasting that into a panel like what you see here. And with this URL of the Phoenix weather file, I'm going to download this weather file using the LB download weather component. All right, so we get the EPW file onto our machine here, right? Here's the path to that EPW file. I'm going to connect that up to our run UWG component here. And I mean, there are a few other options that we have here. You can adjust some of the simulation parameters of the run if you want to. You can change the folder into which the EPW, the morphed EPW will be output. But I'm just going to take all these defaults and I'm going to grab a Boolean toggle. And I'm going to set it to, let's see, I'm going to set it to, well, actually I'm going to keep it false. I'm going to connect it to write and run together. And then when we're ready, I'm just going to set this to true, and that's going to kick off the urban weather generator simulation. So I'm going to fast forward through this next part while we're actually running the UWG. I will see you guys on the other side of it where we'll actually open up the morphed UWG and compare it to the airport one that we have here. So all right, see you guys in a few minutes. Okay, so the urban weather generator finished simulating. It ran through, you'll notice, all 365 days of the year there. And now out of this component here, the urban weather generator component, you'll see that we're getting a kind of, well, two things, a UWG JSON. So the UWG JSON has all the information that describes our urban district, essentially, describes it to the UWG. It includes things like these density parameters and things like the traffic quantity and traffic schedule. But the really important thing that we care about out of this component is this second output, and that is this morphed EPW to account for the urban heat island effect. And you can see that it doesn't have a very interesting name because it's meant to take on the name of whatever model we chose, or in this case, the ID. So if you guys connect up a name for your model, you can probably get a much more interesting name rather than this random string of characters here. But in any event, it's still a valid EPW for this site here. And I want to import the data from this EPW to Grasshopper so I can actually compare it with the rural airport weather file that I have over here. So in order to do this, I'm going to go to the Ladybug tab and grab this LB import EPW component and drop this on the canvas. And you'll see I'm going to connect up our urban EPW to the EPW file of this import EPW component. I'm going to copy and paste this component so that I can also bring in the values for our input airport EPW. And I think I'm just going to compare the dry bulb temperature of these two cases to one another, right? So you got the dry bulb from the airport and the dry bulb for the city center, represented by our model here. So in order to actually take these, preview these values in the grasshoppers, in the rhino scene rather, I'm going to plug them into, let's see, well, I'm going to do a little bit of analysis on them first. I'm going to do this LB time interval operation. And what this will allow me to do is instead of taking the kind of 8760 hourly stream of data, this is just going to average each hour of each month so that I can then more easily see the profile of, on average, how does the urban temperature compare to the rural temperature. So you'll see what this is like in a second. I'm just going to plug in my dry bulb temperature data as my input data for this first right now. And I'm going to copy paste this component and do the same thing for our dry bulb temperature of our airport EPW. And let's see, and we'll go now out of this, we're getting a monthly per hour data collection, right? So this is just going to have 24 values times 12 months. So that's going to be 288. And I'm going to preview this data on our LB monthly chart component. So I'm just going to drop this onto the canvas here. So let me see, I'm going to connect up our, let's see, we'll do the rural data first, I think, connect that up to the data. And then second, we'll connect up the urban EPW temperature on top of that. And so now if I go over to the rhino grasshopper scene, well, it's kind of previewing right on top of our geometry right now. So I'm going to set a base point that's at least going to be a little more to the right. Maybe we'll say 300 meters to the right. So I'm going to just type 300, 0, to then change the base point of this in the scene. There we go. So that's further away. It's not on top of our urban geometry. And let's see, I'm going to go over to top view so I can see this chart a little bit better. Here we go. I got to zoom in. All right. Here we're seeing some useful information. Maybe one last thing I'm going to do. I noticed I have these kind of red lines for the chart, and I'd much rather just see them as black. So I'm going to go to the document preview settings right here in Grasshopper and turn the value down to 0. Okay, so this allows me to see much more clearly what these two dry bulb temperatures look like. And wow, this is pretty interesting. So we're seeing, right, that the urban heat island effect, these two dry bulb temperatures, they tend to be pretty close to each other in the morning, right? But right after we hit the peak of the day, the peak temperature, probably in the afternoon, we start seeing this separation. So it's taking the urban area much, much longer to cool down compared to the rural area, which drops really quickly. Right, and so looks like we hit our peak urban heat island effect. Wow, this is actually really significant. It looks like it gets up to something like, this is 17 minus 12. So, it's almost a 5 degrees Celsius difference between the urban area and the rural area. This is at least in November in Phoenix. And granted, I guess at this time of the year, it's not really that critical. The temperatures in November in Phoenix seem to be relatively mild. Probably we can see the area where the urban heat island effect makes a really big impact is, let's say, in a month like August, right? Because we can see what's happening here for our district. Wow, we almost get, again, that temperature difference of close to, it looks like 5 Celsius between the urban temperature at around 5 a.m. It looks like 5 or 6 a.m. right before sunrise, and that rural temperature. So we can imagine, right, especially when the temperatures are around 36, right? If the urban area is staying around 34 or 34 degrees Celsius instead of cooling all the way down to 28, right? That's going to have a noticeable impact on our air conditioning load, I'm sure, over the course of our nighttime in Phoenix. Right, so this is why it's very useful to have this data as an EPW, right? This urban EPW, it's just like any other EPW file. You see it, you can import it and analyze it using all of the standard Ladybug components, the same ones that you'd use to analyze our airport EPW here. And of course, you can take that and plug that into the energy simulation, right? The same method that we use to run energy simulations with the UrbanOpt component. right? There's nothing that really stops me from taking the urban EPW and plugging this into here, and then understanding then what the energy use would be because of the high density of this rural area, um, right? Instead of just taking this assumption of the airport. Now, I'll give a disclaimer. I know I picked this climate of Phoenix particularly because I know it can have a really intense urban heat island effect, right? Particularly these dry climates that have big diurnal swings, big differences between nighttime and daytime temperatures. That is probably where you're going to find some of the largest urban heat island effects. I mean, obviously, the highest density areas will also have big effects, but more often than not, you'd find in a climate, especially a heating dominated climate like Boston or or where else, or Buffalo, we looked at in the series, you're going to find a much smaller impact from urban heat island on the energy use and on thermal comfort overall. In fact, because those climates are heating dominated, the urban heat island effect usually helps mitigate. It can even reduce the EUI a little bit. But in this case, in Phoenix, I'm sure we definitely see an increase in energy use because of the urban heat island effect. So again, use your judgment. The more that you simulate urban heat island effect like this, the more you'll learn about this and gain an intuition about what drives the effect more than anything else. So now you're at least armed with the tools. I'll give you guys the link to a sample file, the fully finished version of this sample file, so you guys can explore explore the urban heat island effect for yourself if you had trouble following along. Thank you again for following us through this video, and happy simulating of the urban heat island effect.